Hi everybody, this is Dr. Dadu presenting elementary probability 3. Happy listening. Well, I haven't said all that. All we've said concerning the contents of videos 1 and 2. All that remains to be said is unpopular distributions. Just like random variables have types, discrete and continuous, distributions are also discrete and continuous in nature. Here I intend to talk about 4 discrete distributions. The uniform, the binomial, Poisson geometric, and 4 continuous distributions, uniform, exponential, gamma, normal. Starting with the Bernoulli, so far the easiest, commonest. This is his PMF. His expectation is P and his variance is PQ. Binomial. Why binomial? In the binomial expansion of P plus Q raised to power n, this is exactly what we get, and this happens to be the PMF of binomial distribution. Its mean is MP, and its variance is MPQ. Example, in 6 Bernoulli trials of the flip of a fair coin, what is the probability of getting exactly 2 heads? This is 6 choose 2. Probability of heads is equal to the probability of tails, which is 1/2 either way. And the required probability is 15/64. Here is an exercise for you. Poisson distribution. This is the PMF of Poisson distribution. It is unique in the sense that its mean and variance are equal to each other, equal to lambda, its parameter. Example, if the probability that an individual will suffer a bad reaction from injection is 0.001, determine the probability that out of 12,000 individuals, exactly 3, more than 2, will suffer the reaction. For example, 3 is direct, x is equal to 3. For more than 2, you are going to take 1, which is the probability for everything, then remove the 0 case, the 1 case, the 2 case from them. And that's what is exactly done here. See, the 0 case, 1 case, the 2 case. There's more than 2, and that's the required probability. Geometric distribution. Discrete variable x is said to be geometrically distributed. There are binary trials that are continually successful until this failure is experienced. It's said to be geometrically distributed, and the mean is Q over P, and the variance is Q over P squared. The studying student lacks mathematical acumen, can pass with 1/3 and probability 1/3. She has written secondary school mathematics thrice without success. What is the probability that she will pass at the 4th attempt? And that goes on like this. Since she's been failing, as against success. In this case, she's been failing. So we'll write P for Q and Q for P, so that the PMF that we'll use will be this. And after that, the P is supplied to be 1/3 and Q is supposed to be 2/3. So is that the required probability becomes 2/243. Uniform distribution. Random variable x is said to be uniformly distributed in the interval AB if its density function is given to be this. The mean is this, and the variance is that. Example, let the heights of pupils in the primary school be uniformly distributed. Calculate the mean and variance of the heights of the pupils if the shortest and the tallest pupil in the school are 1.2 and 1.6 meters tall, respectively. The mean will be half of the sum of the small heights of the smallest and the tallest. The shortest and the tallest. And the variance will be 1/12 of the square of the difference between the two. That takes us to exponential distribution. Exponential distribution is a continuous distribution, so we'll be needing integration. But I've chosen a particularly easy distribution here so that the integration will not be cumbersome. We are going to use M to denote the required median. So we'll integrate from the list, which is 0 to M. The integration will fetch us this. If you supply the limit, you get this. If you make M the subject, it is this, and evaluate that it is that. So this is the median weight that we are looking for. We can construct a 95% confidence interval in that it will be mu plus or minus T of alpha over 2, then standard times standard deviation. That should be constructed. After, if you construct it very well, it should be this. Gamma distribution. First, we discuss the gamma function, which is denoted by gamma n. It is that enables us to have gamma n plus 1 to be equal to n factorial. You recall we discussed factorial in our sets. Now, a random variable is said to be gamma distributed if the PDF is this. And the mean is that, the variance is that. An example is given, and the solution is there. Normal distribution of the Gaussian distribution. This is the ordinary normal distribution. There are other versions, the standard number, which is tabulated. See, integrals based on this cannot be obtained analytically. That's the essence of the numerical approach that is tabulated by standardization. Now, an example is here for us anyway. In a class, the mean score 58 variance in the past records. Now, an exam is fast approaching. What is the probability that a student will score, any student will score 70 and above in the class? So we standardize to using Z. And this is the sketch. We have our Z to be greater than or equal to 3. So 3 will be somewhere here. This is the shaded region. But what is tabulated is from 0 to this point. So the entire thing, from here to here is 0.5 because this is the positive flank. So if we remove what is tabulated from the 0.5, what is left is the required probability. That's the furthest we will go on probability as a whole. Thanks for listening. Thank you so much, and God bless.